125 amp breaker in the panel board serves as both the disconnecting means and the panel board protection because it is located on the line side of the panel board and rated to protect the conductors and equipment inside the panel board. The National Electrical Code, or NEC, requires that the secondary of a transformer be protected by an overcurrent device rated not to exceed the secondary conductor ampacity. In this situation, number 4 copper conductors, which have an ampacity of 90 amps, are used. Therefore, a secondary overcurrent device rated 90 amps or less should be installed at the transformer to protect the conductors. The use of number 4 copper conductors for the secondary feeder is unusual, as it is typically undersized for a 50 kV transformer. The NEC recommends using conductors that are rated for 125% of the transformer secondary current. For a 50 kV transformer with a secondary voltage of 120/208 volts, the secondary current would be approximately 217 amps. Therefore, the secondary conductors should be rated for at least 271 amps, meaning they should be number 2 or larger. One possible explanation for the use of number 4 conductors is that the original installers may have assumed that the load would be balanced and that the neutral current would be negligible. In this case, the number 4 conductors would be sufficient to carry the load current under ideal conditions. However, it is possible that the load is unbalanced or that there is a significant amount of neutral current, which could cause the conductors to overheat and the breaker to trip. Loose connections and stripped lugs can cause arcing, overheating, and ultimately the failure of the electrical components. In this scenario, the loose connections and stripped lug may have contributed to the tripping of the main breaker in the panel board. Possible causes of loose connections are firstly, improper tightening of the connections, secondly, vibration or movement of the components, thirdly, corrosion or oxidation, and fourthly, faulty components. Properly tightened connections are essential for maintaining a safe and reliable electrical system. Loose connections can create resistance, which leads to heat buildup and the potential for electrical fires. Considering the NEC requirements, let's delve deeper into transformer protection. The primary side protection, in this case the 60 amp breaker, is intended to protect the transformer itself from overloads and faults originating on the primary side. The secondary side protection, ideally located at the transformer, safeguards the secondary conductors from overcurrent situations resulting from faults or overloads on the load side. The 125% rule for conductor sizing is crucial for ensuring that the conductors can safely handle the continuous load, as well as any short-term overloads that might occur. When a 50 kV transformer is supplying a 120/208 volt 3-phase panel, it's important to calculate the full load secondary current accurately. The formula for 3-phase current is kVA divided by volts times the square root of 3. In this case, that's 50,000 divided by 208 times 1.732, which gives approximately 138.8 amps per phase. Multiplying this by 1.25 gives a minimum conductor ampacity of about 173.5 amps. Therefore, number 4 copper conductors are significantly undersized and could lead to overheating and premature failure of the insulation, increasing the risk of a fire. The NEC Article 450 covers transformers and transformer volts, and it provides guidelines for overcurrent protection, disconnecting means, and grounding. NEC Table 450.3 provides requirements for transformer overcurrent protection. This table outlines the maximum overcurrent protection allowed for both the primary and secondary sides of the transformer, depending on the transformer impedance and voltage. In this case, since there is no secondary protection at the transformer itself, the installation does not meet the NEC requirements. The 125 amp breaker in the panel board might provide some level of protection, but it's not specifically sized to protect the transformer secondary conductors, which are the weakest link in this setup. The undersized conductors combined with loose connections create a dangerous situation. Loose connections increase resistance, causing heat buildup. This heat can damage the insulation of the conductors and the terminations, leading to arcing and potentially a fire. The strip lug indicates that the connection was likely not properly taut during the initial installation, or that the lug was damaged over time due to vibration or corrosion. The arcing observed at the loose connections is a clear sign of high resistance and potential insulation breakdown. Replacing the lugs and tightening the connections is a temporary fix, but it doesn't address the underlying issue of undersized conductors and lack of secondary protection at the transformer. To properly rectify the situation, firstly, install an overcurrent protection device such as a circuit breaker or fuses at the transformer secondary, sized according to NEC table 450.3 and not exceeding the ampacity of the secondary conductors. Secondly, replace the number 4 copper conductors with conductors that are sized to carry at least 125% of the transformer's secondary current. Refer to NEC table 310.16 for conductor ampacity ratings, considering the conductor insulation type and ambient temperature. Thirdly, ensure that all connections are properly torqued using a calibrated torque wrench according to the manufacturer's specification. This will help prevent loose connections and ensure a good electrical connection. Fourthly, inspect the panel board for any signs of damage or overheating. Replace any damaged components, such as breakers or bus bars, to ensure the panel board is in good working condition. Fifthly, perform a load calculation to determine the actual load on the transformer. This will help verify that the transformer is properly sized for the load and that the conductors and overcurrent protection devices are adequately rated. Sixthly, consider installing a transformer monitoring system that can detect overloads, overtemperatures, and other abnormal conditions. This can provide early warning of potential problems and prevent equipment failure. Now let's address the question about why the original installation might have had number 4 feeders. It's possible that the original design was based on an incorrect load calculation or a misunderstanding of the NEC requirements. It's also possible that the load has increased over time, exceeding the capacity of the original conductors. Another possibility is that the original installers were trying to save money by using smaller conductors, which is a dangerous and potentially illegal practice. Regardless of the reason, it's crucial to correct the situation to ensure the safety and reliability of the electrical system. The location, Federal Way, Washington, may have local electrical codes or regulations that are more stringent than the NEC. It's important to check with the local authorities to ensure that the installation complies with all applicable codes and regulations. In summary, the installation in question has several deficiencies that need to be addressed to ensure safety and compliance with the NEC. The undersized conductors, lack of secondary protection at the transformer, and loose connections all contribute to a hazardous situation. By following the recommendations outlined above, the electrical system can be brought up to code and provide reliable power to the freight terminal operation. It's crucial to remember that electrical work should only be performed by qualified and licensed electricians who are familiar with the NEC and local codes. Working with electricity can be dangerous, and improper installation or repairs can lead to serious injury or death. Always follow proper safety procedures and use appropriate personal protective equipment when working on electrical systems. Remember to always energize the circuit before working on any electrical components, and use a voltage tester to verify that the circuit is energized. If you're not comfortable working with electricity, it's best to call a qualified electrician to perform the work. Transformers are essential components of electrical distribution systems, and it's crucial to understand how they work and how to protect them. By following the NEC guidelines and best practices, you can ensure that your transformer installations are safe, reliable, and compliant with all applicable codes and regulations. In addition to the above considerations, it's also important to consider the ambient temperature when selecting conductors and overcurrent protection devices. The NEC requires that conductors be derated for ambient temperatures above 30 degrees Celsius or 86 degrees Fahrenheit. This means that the ampacity of the conductor must be reduced to account for the higher temperature. Similarly, overcurrent protection devices must be selected based on the ambient temperature to ensure that they will trip at the correct current level. If the transformer is located in a hot environment, such as a freight terminal, it's important to select conductors and overcurrent protection devices that are rated for the appropriate ambient temperature. Another important consideration is the type of load being served by the transformer. If the load is nonlinear, such as computers, fax machines, and lighting equipment, it can generate harmonic currents that can overload the transformer and conductors. In this case, it may be necessary to use a K-rated transformer, which is designed to handle harmonic currents. K-rated transformers have a higher insulation temperature rating and are better able to withstand the effects of harmonic currents. It's also important to use appropriately sized neutral conductors to carry the harmonic currents. The NEC requires that the neutral conductor be sized at least the same size as the phase conductors for nonlinear loads. In some cases, it may be necessary to use an oversized neutral conductor to handle the harmonic currents. In addition to the above considerations, it's also important to consider the voltage drop in the conductors. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. The NEC recommends that the voltage drop in the conductors not exceed 3% for power circuits and 5% for lighting circuits. To minimize voltage drop, it's important to use conductors that are large enough to carry the load current without excessive voltage drop. It's also important to minimize the length of the conductors and to use conductors with low resistance. In addition to the above considerations, it's also important to consider the grounding of the transformer. The NEC requires that the transformer be properly grounded to protect against electrical shock and to provide a path for fault current to flow back to the source. The grounding system should be designed to provide a lower impedance path for fault current to flow back to the source, which will cause the overcurrent protection device to trip and to energize the circuit. The NEC Article 250 covers grounding and bonding, and it provides guidelines for grounding transformers and other electrical equipment. It's important to follow the NEC guidelines to ensure that the grounding system is properly designed and installed. In addition to the above considerations, it's also important to consider the maintenance of the transformer. Transformers should be inspected regularly for signs of damage or overheating. The connections should be checked for tightness, and the insulation should be inspected for signs of deterioration. The transformer should also be tested periodically to ensure that it is operating properly. Regular maintenance can help prevent equipment failure and can extend the life of the transformer. If the transformer is located in a harsh environment, such as a freight terminal, it may be necessary to perform more frequent maintenance. The environment can expose the transformer to dirt, dust, moisture, and other contaminants that can damage the transformer. Proper maintenance can help protect the transformer from these contaminants and can ensure that it operates reliably for many years. In addition to the above considerations, it's also important to consider the energy efficiency of the transformer. Energy-efficient transformers can save money on electricity bills and can also reduce the environmental impact of the electrical system. The Department of Energy has established minimum energy efficiency standards for transformers, and it's important to select transformers that meet these standards. Energy-efficient transformers use less energy to operate, which can save money on electricity bills. They also generate less heat, which can reduce the cooling load on the building. By selecting energy-efficient transformers, you can reduce the energy consumption of your electrical system and help protect the environment.